Okay. Okay, for those that came late, the exercise we are solving, it's in this folder. Okay, the class files, today's date, and these two. This is the description of the exercise, and that's the actual Excel file. Okay. And I suggest you do this frequency analysis in another sheet, okay, in another Excel file. So you do your simulations, you copy only the NPU column, paste it on a new sheet, and then do frequency and everything on the new sheet. Okay, you will see probably why soon. Okay, row only, you have to put a $sign in front of the number. Okay, but that means if I change now to this column, it will use now column D, okay, and then it will use E and so forth. Okay, that means it will use all the time, will change these two numbers. Okay, this one you have to use this triangular, so it doesn't really matter, but you have to make sure to block these numbers such that when you drag it down, it won't shift on the row. Okay, after you have done that, actually you see this sheet becomes very heavy. Okay, because it has this volatile function. If you see, I think we did it last time. Not the compressor, we already forgot about the compressor. Okay, it has something saying that every time you make any small change on the sheet, it should recalculate. Okay, that's what it's saying. So you apply a random number, and every time you do a change, it should automatically change. So that's why this sheet becomes extremely heavy, because anytime you do something, open a new sheet, change a cell, everything is going to change. Okay, so you see that your computer gets frozen for a while computing all of these numbers, and then it starts working again. Okay, so that's what I told you. Then you copy this column at the end. Okay, remember that was one of the bases of Monte Carlo. You make a lot of random samples. Let's see here. Okay, you make a lot of random samples, you compute that number, and you do it many times. After that, you take this cluster of results, all of this column of results, and then you apply this frequency analysis. Okay, that we have discussed, I think, actually here at the beginning. Okay, we apply this frequency analysis. Some things that are useful to remember here: when doing the counting, you have to select the whole column. Okay, then you have to apply frequency function, and then you have to say Control Shift Enter to apply it with Control Shift Enter. Okay, and after that we calculate. At least that's what I got. I hope you got a similar numbers. Otherwise, either I'm wrong or you're wrong. Okay, but basically minimum, that's the minimum I got. You might have gotten a different number. And if I increase the number of samples, 1,000,000, 10,000, this value should converge for all of us. Okay, because your computer generates a different random number than my computer. Okay, but it should be at least on the ballpark, 50 million and 279 million. Okay, the maximum. Is it in the ballpark for your numbers? Yeah. Okay, I decided to use 20 beans. Delta will be 12 million in that case. And then those are more or less my results. This is the frequency, the output of the frequency function. Okay. Then the PDF is simply, it really doesn't represent anything, but it allows you to identify which is the most probable number, which is the number that comes up the most. Okay, which is this count divided by the total number of samples. And then the inverse CDF, remember the CDF, we do it from here, and you sum up, accumulate, compound from the top. Okay, the inverse CDF, and that's what we call in petroleum engineering the expectation curve, we sum actually from bottom up. Okay, and that's the values I got. So you see, where is the mean that I calculate? In this case, I say is the average mean. Okay, I don't write it here, but I calculate it here. The mean that I got was, and this is the arithmetic mean, 1.27 e to the 8. Standard barrels. And that PDF tells you very clearly minimum, maximum, the mean, which is 120, will be something like here. Okay, and where is the mode, or what is the mode?
Which has highest frequency.
Okay, the one which has the highest, we call it probability, right? Because here we have been saying frequency, because we have some numbers over which we calculate this frequency. Okay, but actually all of this is guessed. Okay, all of this is like, so all of these are probabilities, okay, in a way. So that will be the mode here. And it's not a smart way, but if you say, well, that's the most likely number that will come up, okay? And you see that the distribution actually resembles this distribution is called a log normal, okay? It's a log resembles a log normal distribution, okay? You know, a normal distribution actually looks symmetric, okay? It's like a Gauss distribution, and log normal simply skewed to a side, okay? But distribution of reserves are actually usually log normal, okay? And then we calculate the inverse CDF, which is this one, okay, or what we also call the expectation curve. Expectation curve of TRR. Okay, and here there are three numbers that are typically used in petroleum engineering or in field development. Okay, the three numbers are P90. Okay, what is the meaning of this number, or what is P90? P90, I go 90 here on the graph, knock it, and then go down. Okay, that means that I have my reserves in my field. There is 90% probability that I have at least that number, or less than that, or higher than that.
At least, yeah, minimum
Is it okay, at least I have that number or higher, okay? Because here I'm 100% sure that I have at least that number or higher, okay? Because that's the minimum, right? So P90 really saying that I have at least that number or higher, okay? So there is 90% chance or 90% probability that research the field equal or greater than this value, okay, this P90. And if you ever forget, you say, how do you sum these probabilities? Okay, here you have all of them, okay? When you go to the extreme. Here you have none, okay? That means that there is no chance actually, or zero chance that your reserves are greater, okay? They can be smaller. They're 100% chance that they're going to be smaller, but here this is telling you is zero. That means the chance that they are higher than this number, okay? If you forget, go to the extremes, see what is the CDF on those extremes, and then from there you kind of find out what is the chart telling you, okay? This one we call it proven, okay? Proven reserves. And we don't sometimes, every company uses slightly different number, okay? They can use 85, they can use 80%, so don't be fooled. They call it proven reserves. Also they call it downside volumes, okay? Or downside estimates, also known as, okay? Then we have the second number, we have P50, which we again come here with 50 and knock it down, okay? That will be P50, and 50 is exactly the same, 50% chance, 50% probability that the field has reserves equal or greater than P50. And this number is sometimes used for everything, okay? If you want to use a number to calculate production profiles, if you want to calculate cost, if you want to calculate, usually this is the number, the magical number. That's what they use for everything. And we are not sure that's the best number, but that's what typically people use. Okay? And this is called the proven plus probable reserves. Okay? Or sometimes calls the best estimate. Okay, which I told you is not, that number doesn't tell you really the most likely. Okay, or you have a distribution, that's what you have. Okay, you can get very lucky, you have the high case, and you can get very unlucky, you have the low case. But there is some indication that that might be the most likely. But be careful, don't call it I don't like this name, the best estimate. Okay, because really we don't have a way of knowing. There is no estimate actually. Okay, and finally, for those that are very, very optimistic, okay, we have P10, can be P20, P15, P5. Okay, just be careful with this number. And there is 10% probability only that reserves, and I can do this with reserves or in place. If I take the recovery factor out of the picture, that will be in place. Okay, that reserves are equal or greater than P10. Okay, and how do I call this guy? I call it, these are the proven plus the probable plus the possible. Okay, and they're also called the upside volumes. Okay, upside or optimistic. Okay, so each company country, so let's put the comment here also, I think it's important. Each company uses different percentage. Okay, maybe you have to report to the stock exchange, so then they fix, you have to use this percentage. Or maybe you are, I don't know, in Norway, so each company they call it, oh, is the best estimate, or is the upside, or is the downside. But you have to know what do you mean by the downside? Which percentage are you using? Okay, always be sure. But the safest is if they give you the distribution. Okay, they try, instead of giving you the curve, that's difficult for people to assimilate. They say, oh, what do we have here? We don't know, so they give these three numbers instead of giving the distribution. Okay. And just some examples from some, that's the PDO of a field in, that's Hebron, that's the one that you have. I think both of them you have. Okay, so you see in each block they have the upside, that will be P10, best estimate P50, and downside the P90. Okay, instead of giving the distribution, they give these three numbers. Okay, while you have other PDOs where they actually try to make a better work. Okay, they give you actually the whole distribution, and then you can do whatever you want with it. Okay, frequency, in this case you see this is maybe number of counts, and then you have the mean, in this case the mean and the mode, they are quite similar. It looks more like a normal distribution for some reason. Okay, that clear? Okay, now let's do it. Let's take a break and let's try to do it with Python. But there is one thing, there is one equation that is sometimes used to calculate how many iterations. Okay, sometimes you simply use brute force, you increase 10,000, you increase 1,000, 5,000, 10,000 and see your results don't change much, okay, the P90, P50, P10, and you have to specify some error. So that's trial and error, or what we call, maybe not, let's not call it trial and error, but we say convergence study. Okay, that's how mathematicians call it, convergence study. Okay, so you say number of iterations, and then you calculate P90, P50, P10, maybe you say also the mean, the mode, okay, and you simply increase number of iterations until these guys don't change much from the previous. And you should see with number of iterations the P90 initially is changing quite a lot, but then it becomes constant. Okay, and that's if this is within your error, this is the number of iterations that you want. Okay, within, for example, variation, you estimate a band. I don't want it to change more than 3%. Okay. You have to do this for many things. Okay, reservoir that is plus minus 3% error. Okay. You do it in every stage of life. You do it in reservoir simulator to know the optimal grid size. You will use it for many things. So you should use it also here. There is also one equation that sometimes people use that looks a bit like that. Number of iterations is a factor times the standard deviation divided by the error, okay, squared. Okay, that is the standard deviation, but that's assuming you already have a sample. You have already done a simulation, a Monte Carlo simulation. Okay, this factor depends on the forgot the name in English, sorry for that. Confidence okay, okay, depends on the confidence. Level, okay, and it's usually a number between 2 and 3. Okay, if you have 95 or if you have 98, will be 3. You want 98% confidence, so that means that the interval has to be very slim. Okay, so then you use 3. Then the number of iterations have to be bigger. If you want 95 or 92, then you can use 1.8, 2 point something. Okay, for example, is this factor, if it's 98% confidence, is like 3, but if you want 92%, I think it's like 1.8. Okay, then this one you have a certain number of samples where you calculate the standard deviation, and the error is the average usually times how much you want the error to be. Okay, and this is related to this 3%. So times this error, which is can be, for example, 0.03. This is a 3% error. Okay, and from there you estimate, having some iterations, that's how you estimate the number of iterations you need. And if you calculate they are more than the ones you have, then you have to run more iterations. Okay, if they are less than the ones you have, then that's fine, that you are okay. Okay, but it's basically you need to have done a simulation. Okay, you need results of a simulation. Let me make that's a bit messy here, sorry for. Okay, so let's say here, having results of at least one simulation with n samples. Okay, and then we say if n is greater than number of iterations, then number of iterations, then n is appropriate. If n is actually less than the number of iterations, then n must be increased. Okay, and remember here n, we're not saying in place, but it's actually number of samples. Okay. Okay, but you use a number, 2 and 3, the standard deviation of your sample, and the average of that sample, and some error that you specify, some error band. Okay, 2-3%. But if you want more details, this is on this page 113 of the compendium. Okay. Okay, let's take a break, and then let's see how far we get, but try to solve it with Python. Okay, the same. But let's take a break. Let's try to make it short, 10 minutes. Will that work for you? Yeah. Okay. Okay, so I hope all of you have created an account in this website called CoCalc. It's simply to be able, it's like a remote computer where you're able to run Python scripts, okay, or Python code. And the good thing about it is that it is a remote computer, it already have a series of things that are pre-installed that we don't have to do on our computer. Okay, so let's that's the main page you get when you sign into CoCalc. So we're going to create a new project, and let's call it because we have the basic account, we cannot collaborate, I cannot share it with you, but let's call it simply class problem, and then maybe we say estimation, TRR estimation. Okay, that will be our project. Okay, after I have created the project, you see you can have several files under that project. You can do other things. So let's just create a file. How do we call it? Let's call it Monte Carlo simulation. Okay, because that's actually what it is, right? And what type of file is it going to be? We're going to use, there are different ways I can run Python code, okay? But one of them, you will see how it looks now, is this Jupyter notebook. It's like an interactive way to run Python code. I split it into codes, into blocks, and then I can run each block separately. And I can also output live what the code is doing. So it's a simpler way to do debugging and to see what's happening on the code. So let's see, Jupyter notebook. Okay, we're going to use Python 3. Python, it has several versions that are used, but the current version is Python 3. Okay. We select it, and finally we got into the Jupyter notebook. Okay. These are the blocks that I told you, and I can have many blocks. So for example, I can write print, and and then I simply execute these blocks. Still the machine doesn't know what to do with it, okay? Because now if you run it, okay, it just printed hello world. It's doing what you're telling the cell to do. Okay? So now we go back to this cell. You see now it switched automatically to that cell. The machine thought, well, now you're done with that previous cell, okay? But now we know when we are programming, we are going to make mistakes, and we're going to, have to go back to things and fix it. So the first thing we're going to make, and for that it's helpful to make a comment. Comments are made with this hashtag, okay? And you say first, let's say importing needed libraries. Okay, that's the first block. That's what it's going to make. Okay, and we're going to use 3 libraries. We're going to use let's use 2. I think we won't have time to use 3, but we're going to use something to plot. Okay, which is called matplotlib.pyplot has plt. So the syntax here is that I'm importing, that's the name of the library that I'm importing. It's called matplotlib and it's simply for plotting. Okay, and I'm importing that library has plt. So every time I need that library, I don't have to call it by its full name, but I can call it with this kind of reduced name. Okay, and we can add a comment. If we really are beginners in Python, we can say library for plotting so that we remember. But after with time, if you have been using Python many times, you know matplotlib is for plotting. Everybody that uses Python will be able to identify what that library is for. Okay, then we say import. The next library we're going to use is NumPy, which is actually exactly what the number stands for, numerical Python, and it's a library to make a lot of numerical things in Python. Okay, matrix manipulation, vector multiplication, vector operations, all kind of things. And this library has actually this random number generator, okay, that we are going to use. Like in Excel, you had this VBA function that I gave you, right? X uniform. This library already has it pre-programmed for you, so we don't have to program that part. Okay, NumPy, and say has np. That's the name that we are going to use when every time we need to call NumPy. And let's import this library. This is for making a table, okay, but we are not going to use it. I think today we won't have time. Okay, pandas, which is this is for creating tables, and this library is for numerical operations or for math operations. Okay, after we have that, I suggest we keep it clean. We say each block has a function. Okay, this block is to create import libraries, so we are not going to import anything else, and we run it. Okay, and I got no error message. That means that the server, or these guys CoCalc, they have all of these libraries installed. Okay, which is nice. That's exactly what I needed. Okay, next step, next block, what I'm going to do on this block, I say declare functions. What function do I need here? Yeah, NPU, the TRR, right? Because we have the function we said the NumPy will take care of the uniform sampling, triangular sampling. Okay, so the only thing we need here is the function that is not included in any library, okay, which is the NPU equation. Okay, so I call to define a function just like in VBA. Instead of saying function, I write def. Okay, then I say NPU, and NPU is a function of porosity, rock volume, net to gross, saturation, BO, and recovery factor, I think, right? Very careful. Python, after you declare a function, you have to use 2 points, then enter, and you see automatically it make a tab, okay? Because that's what it's saying. Everything inside this line will be my function, okay? It knows that now you're about to declare a function, and it makes this tabulation, okay? VBA is simply ornamental. It's simply to let us know that this is inside a function. You can have it or not have it. It won't affect your code. But in this case, you need to have it. Python depends on that space to let it know everything inside here is declaring the function. Okay? So I think first we should put some clarification. What is POR? Is porosity in fraction. Then we say RV is rock volume in, we can either have it in standard barrels or standard cubic meter. Net to gross is net to gross in fraction, right? What else? SO is oil saturation in fraction. Just simply, if someone is taking this code and wants to use it, that knows exactly what do you mean by all of these variables. Okay, PO, oil formation, volume factor, and this will be in barrels per standard barrel or cubic meter, standard cubic meter. Okay, and FR is recovery factor in fraction. And finally, I have to say what to do with all of these things. Okay, so I say calculate, let's call it original oil in place. Okay, this will be porosity times RV times, and be careful, I have to use exactly the same spelling, net to gross times SO times FR divided by BO. Okay, and then finally, after I made that calculation, I say return original oil in place. Okay. You could have done is simply copy this guy and paste it here, okay, without having that extra line. But it's cleaner, at least to my opinion, to have it. You do the calculation inside the function and then you return it in the last declaration. Okay. So now we have our libraries, we have our function, and now we need to make the input for the Monte Carlo simulation. Okay. Again, I run it. No errors. It didn't complain. So far, so good. Okay, so let's call this one input data. What do we need for our simulation? If you remember the Excel sheet, everything that was in red was the input. So we need for each variable minimum, maximum, and for the recovery factor we need 3 values. Okay, minimum, maximum, and mode. Okay, so let's start typing. This is just a bit boring. Okay, so we say porosity minimum. Let me just make it small. The porosity minimum is 0.18. Porosity maximum, that will be 0.3. Then I come to RV minimum is 5 e to the 9. Let's work better in million barrels. Okay, so let's call 5 e to the 3, and this RV will be in, okay, here it actually doesn't matter, but here it's, let's say this rock volume is in million standard barrels. Okay, just to avoid having such big numbers. RV maximum, how much is it? 6.25. Okay, next is net to gross. all boring. Simply I'm just creating variables that define the minimum and the maximum for each parameter. Okay. So BO and in recovery factor we have actually a minimum, we have a maximum like for the others, but actually we also have a mode. Okay, we have a triangular distribution for which is 0.25. So you see, Excel is a bit more graphical. You can have all the input there, everything is in red color, so you see exactly what you're inputting. In Python you have to be careful. You're putting it has a bunch of lines, so you have to be like, it's a bit more difficult to process by the brain, but it's exactly the same thing. Okay, instead of using this table, I'm using declaring these variables. Okay, so let's make sure we didn't screw up any place. 625 gross, SO min, SO max, BO min, BO max. Okay, that's my input data. That's everything I need, right? Based on these numbers, I'm going to generate the samples. Okay, so I just run this cell. Okay, no errors, which is nice. Next, what is the next step? The Monte Carlo simulation, right? And the first step in the Monte Carlo is actually the sampling, right? Random sampling. Okay, how many samples are we going to use? We are going to call them n. Okay, the number of samples. How many samples should we use? Let's use, like we use now, 1,000. Okay. Now, sampling each variable, I do it by the following way. I create a vector, okay, and that vector I'm going to have simply with the name of each variable. Okay, but this in this case will be a vector of porosities, of 1,000 porosities. So that to sample, I have to use that library called NumPy. Okay, and I have to access a module inside that library. Okay, and to access that module, I say NumPy dot. That's, I'm going under the library, and I'm going to under a module called random. Okay, and inside the random, it is not any random, but it's actually a uniform distribution. So I have to put another point and say uniform. Okay, so that's the library name, like a module inside that library, and then like one more level in a function inside that module. Okay, so that means I want a random sample using a uniform distribution. Okay, and then I say, please select a random sample from porosity minimum to porosity maximum and take n samples. Okay, and just before we go through the other variables, okay, let's make a test. Let's say print this porosity to see what do we get. Okay, and let's run that cell. Okay, and actually you got all that bunch of numbers that we make a simple check should be between 0.8, 0.18 and 0.3. 1,000 numbers. Okay. I created a vector with all of these 1000 numbers, and all of them are random. They don't have any order, simply were randomly sampled between 0.18 and 0.3. Okay. Next step, I do the sample to all the rest. Okay, RV, exactly the same. Maybe we can copy the same equation, right? What is the next? Net to gross, SO, and BO. And here simply have to change these two, RV. You see that it still keeps these numbers because I haven't run it again. So it simply has the output of that block is the previous run that I made. Okay. So after I run this, it will simply clear it out. Okay. Now, what am I missing here? The recovery factor, right? FR. And FR is np.random, but now it's not uniform. Okay. It's triangular. And if you search for, you get actually the library of NumPy. Okay, you search on the internet and you see NumPy random triangular, and it's using the left, the minimum, the mode, and then it's using the right. Okay, left should be less than the mode, should be less than the right. Okay, so just like we did before, we say recovery factor mean. What was next? Left, mode, and right. Okay, FR mode and FR right. Max. Okay, not right, max. Okay. Just to check, we come and we say plot. Sorry, simply FR. We run it. Okay, we have to put the number of samples, right? Otherwise it's going to sample just one number. 0.23, this should be between 0.18 and 0.35. Yeah, 32, so you see it's actually making the sampling. Okay. Next step, I have all of my samples now. I created a lot of vectors with all of these variables. What is the next step? Simply Monte Carlo simulation, compute NPU for all samples, right? How do I do that? I say, sorry, this should be here, not initial oil in place, but TRR, right? Because it's not only the in place, but you have already the recovery factor. Okay, total recoverable reserves are equal to that function NPU, right? And it's going to use, for convenience, I have used the same names, okay, that the variables. So you simply have to copy and paste this guy here. So in this case, this NumPy is smart and is saying, well, all of these are NumPy vectors, okay? And this function is actually applied to like a single variable, simply a value, right? But I'm smart and I'm going to apply that to all the first element, all the second element, all the third element, and I'm going to give the user simply a vector of TRR, okay? So it's applying that to the first element of porosity, first of RV, first of NTG, first of SO, first of BO, first of recovery factor, and then it's going to have, that will be my first element of TRR. Then go to the second, calculate the second. Exactly what we have done in Excel, simply now it's like a vector operation. Okay? Compute, maybe we should say here, so simply to calculate TRR, to print it, to make sure everything went fine. Okay, and it's actually an array from 82,109,139. Okay. What do we have to do next? Frequency analysis, right? Exactly what we have done in Excel. We come and we apply frequency analysis on TRR. So that will be my next block. But I think we have reached the end of the lecture. So okay, so the next block will be frequency analysis, but that we take it on Friday. Okay? I didn't want to show you like some maybe we'll do it on Friday, but some fundamentals about Python. Why is it different than other programming languages? Why are we using it in class? I went straight to the code. Okay? Any question before we close? No? Okay, see you on Friday. And we finish this exercise. Have a nice week.